For most of us, this is what interacting with AI looks like: a sleek, highly responsive interface where you type a prompt and watch a language model spin up text that feels entirely magical. Right now, the vast majority of application development is happening exactly here. Developers are building entire products by engineering text prompts and routing them through these highly visible generative models. But treating this interface as the entirety of AI is a massive liability. That generative layer is just the surface. Beneath it sits a four-tiered infrastructure: deep learning, then machine learning, and at the bedrock, pure computer science fundamentals. If you only know how to operate at that top generative layer, you will quickly hit a hard boundary. Try feeding a massive spreadsheet of structured numerical data or hours of raw audio and video into a standard text prompt, and the system breaks down. Then there is the economic wall. Relying exclusively on a third-party API to process every single user interaction becomes exceptionally expensive the moment an application scales its user base. When an application built entirely on prompts inevitably fails, a developer restricted to that top layer has no mechanics to debug the underlying architecture. They can only rewrite the prompt and hope for a better output. Building resilient, cost-effective, multimodal applications requires moving past simple prompting. It requires an engineer to move down the stack and master the mechanics of deep learning and machine learning directly. You cannot treat AI as a magical black box. It is an interconnected, optimizable vertical stack, and you have to know how to pull the levers at every level. To understand why we need the lower layers of that stack, look back a decade. AI researchers at the time were hitting a severe data ceiling with traditional machine learning models, like logistic regression and decision trees. This chart shows how those models responded to scale. On the x-axis is the amount of data, and on the y-axis is the model's performance. As you can see, traditional machine learning algorithms initially improved, but quickly and permanently plateaued. They failed to utilize massive datasets. You could feed tens of thousands of hours of audio data into an older speech recognition model, and the accuracy would not move. The algorithm simply did not know what to do with the excess information. The architectural solution that broke the ceiling was the neural network, which forms the foundation of the deep learning layer. Neural networks possess a distinct mathematical advantage. They follow a continuous scaling law, meaning that as you feed them more data, their performance actually continues to improve. And if you scale up the physical size of the network, moving from a small neural network to a medium and then a very large one, the resulting performance reaches exceptional heights. The more data and compute you add, the better the prediction gets. Sustaining this upward trajectory requires immense physical compute power, specifically modern GPUs in dense server farms to process billions of calculations. Neural networks became the undisputed core of modern AI because they provided the only predictable mathematical recipe for absorbing limitless data. Now, let's look at how this data appetite relates to the full abstraction stack. Generative AI, specifically the transformer networks powering modern large language models, is simply a highly specialized sub-branch of deep learning. It is heavily optimized for processing text in and generating text out. That specialization introduces the first major engineering bottleneck: modality. When an application needs to analyze unstructured data, like processing raw image or video files, those top-layer text models become highly inefficient and, in many cases, entirely useless. The same limitation applies to highly structured, non-text information. Feeding massive, interconnected numerical spreadsheets into an LLM will quickly break the generative layer's logic. The engineering solution is to bypass the generative layer completely. Developers must drop down a level and apply targeted deep learning models, like convolutional networks for computer vision, directly to the raw data. An engineer who strictly relies on text prompting will inevitably hit a hard capability wall the moment the real world demands diverse data inputs. The second major bottleneck strikes exactly when a prototype succeeds: exponential scaling costs. This chart graphs user volume against operating costs. Running large third-party foundation models for every single query means that as your user base grows, your API billing curves violently upward into catastrophic territory. No amount of tweaking or refining a text prompt can fix a systemic infrastructure cost. You are paying for massive compute cycles you don't actually need. The solution requires dropping into the deep learning layer. By utilizing techniques like hyperparameter tuning, engineers can fine-tune smaller, open-weight models trained specifically on their own data. These highly customized, smaller models can frequently match the prediction accuracy of massive LLMs, but they execute at a fraction of the compute cost. Mastering the deep learning layer is the primary defense mechanism against the prohibitive economics of the generative AI API market. Dropping into the deep learning layer also requires a shift in how applications are built. In traditional software development, the code dictates the outcome. But with machine learning, the output is dictated heavily by the chaos of real-world data. You control your code perfectly, but you cannot control what users feed it. A cleanly coded speech recognition model will break instantly when it encounters unexpected background noise, multiple overlapping speakers, or unique regional accents. This chart illustrates the prototyping loop. Since the data is inherently unpredictable, the only way to map it is to build an experimental sandbox where code and data collide, exposing the edge cases immediately. Modern AI-assisted coding tools are exceptional at this. They allow engineers to execute these rapid iteration loops faster than ever before, generating quick test environments to map out data failures. This rapid iteration must be handled responsibly. The sandbox environment ensures that sensitive user information remains secure and isolated while the engineer tests the model's boundaries. Rapid prototype development is a rigid technical requirement for surfacing data anomalies that would otherwise remain hidden until a full-scale failure. The rise of these AI autocoders has created a severe professional anxiety, a belief that basic programming skills and core computer science fundamentals are suddenly obsolete. History points in the exact opposite direction. When humanity moved from punch cards to keyboards, or from assembly language to higher-level code, every abstraction layer that made programming easier ultimately increased the demand for deeper technical understanding. We are facing a paradox of automation. As AI successfully automates the generation of basic syntax, the ability to architect complex logic across the full abstraction stack becomes the true bottleneck. To get an AI agent to build a robust, multi-layered application, the human engineer must possess a rigorous vocabulary of computer science and deep learning concepts to properly direct it. An engineer whose entire skill set consists of writing vague prompts cannot instruct an AI assistant to debug a highly specific memory leak, nor can they diagnose an error in hyperparameter tuning. They lack the language of the machine. The ultimate state of a modern engineer is utilizing an AI assistant as a high-speed tool while retaining total architectural command over the lowest, most complex layers of the stack. In the age of automated generation, true productivity belongs only to those who understand the raw fundamentals well enough to command the machine with absolute precision.